Okay, so hello everyone, welcome. Can you hear me? Okay, thank you. Just waiting 1 minute, then we'll start. Okay, so we'll start today's session. So basically, today is our fourth number test, and I hope all of you already get all of regular class for the previous session for first day, second, and third day. So basically, today's session I will discuss about that mainly LST, then as well as also urban heat island, and also urban heat island effect, how we can easily monitor. Okay, so we'll start. So let me share my screen. And after completing the 3 hours live training, then we talk about the problem solving for 1 hours. Okay, so let me share my screen. Okay, can you see my screen? Is it visible? Okay, thank you. So basically, today's session I try to discuss about that this type of topic, mainly how to remove cloud and haze from satellite images. So basically, when you want to work with rainy season, we find out a lot of cloud in our satellite imagery, and cloud is very unnecessary pixel. So this type of pixel basically destroy your calculation or destroy your result. So that's why it's very important part to get the very neat and clean satellite imagery for any purpose for remote sensing work. So today's session discuss about that how we can easily remove the cloud and haze from the satellite imagery, both of satellite imagery such as Landsat and Sentinel, both of satellite imagery, how we can easily remove all of cloud and haze and get the very neat and clean satellite imagery. We also discuss about that, as well as we'll discuss about the DEM, mainly digital elevation model, how we can easily use the DEM data and create the different types of terrain profile, such as hillshade map, then slope map, or aspect map, or hillshade view map. So this type of terrain profile, how we can easily use using the DEM data, mainly we can easily find out the DEM data, NASA SRTM DEM or ASTAR DEM. Okay, so both of data we can easily find out in the Google Earth Engine data catalog. So both of data I will try to show you that, and then how we can easily make the DEM, and using the DEM how we can easily create the different types of terrain profile such as hillshade map or hillshade view map or slope map or aspect map, how we can easily create using Google Earth Engine. We also discuss about that, and also discuss about the land surface temperature. Basically, we already create the land surface temperature using MODIS satellite imagery. But today's session I discuss about the Landsat, because Landsat is more good than Modis. Okay, because Landsat is the resolution is high than Modis. So that's why we can easily get the result for that very better map or very better LST, mainly land surface temperature result, when you are using the Landsat satellite imagery. And Modis, we already discussed about that. Modis is basically one kind of ready-made product. Using the ready-made product, we can easily make the LST. We already done this part. So today's session, I discuss about that how we can easily use the Landsat satellite imagery and make the LST, mainly land surface temperature monitoring. And further, we'll also discuss about that how to calculate average, maximum, minimum NDVI for any specific region, as well as how to monitor the urban heat island. Basically, LST and urban heat island is the very close to related. So that's why I also discuss about that how we can easily identify for the urban heat island using the Google Earth engine, use the Landsat satellite imagery, as well as we discuss about the urban thermal field variance index. So this is one kind of index. This index help you to get the what the scenario, what the impact, or what the effect of urban heat island. We can easily monitor using the UTFVI index, mainly urban thermal field variance index. We can use, as well as we also discuss about the time series chart, basically LST time series chart, how we can easily create using Landsat satellite imagery. Okay. So first of all, one by one, we try to discuss all of topic. I hope we can easily get the all of idea. Let me open my slide. So first of all, we discuss about that LST monitoring using Landsat satellite imagery. Okay. So this is one kind of map for the Dhaka city study area. So from this map, we can easily get it where the high temperature for land surface, where the low temperature, we can easily get it from this map. And this map we generate using Landsat satellite imagery. So if you search on the Google or any ResearchGate profile or Google Scholar, you find out a lot of papers. Suppose I simply search on the Google LST monitoring using Landsat 8 satellite data. So you find out this type. Suppose I simply open this paper. So this is one kind of paper for this is the contribution of Landsat 8 data for estimation of land surface temperature in Batna city, eastern Algeria. So basically, we find out this type of algorithm. So here you can see this is the Landsat 8 data. So basically, this is the algorithm about that. So this is the algorithm for monitoring the LST. Not only for that, if you search other paper, so if you simply go to the suppose ResearchGate profile and simply search some paper regarding the LST, so you can also check the other method or other methodology. So simply search LST monitoring Landsat. I simply search here this type of keyword. So we find out this type of paper here. You can see there's a lot of paper regarding the Landsat and LST, land surface temperature. Suppose randomly I just open one. Suppose just I try to open it. Land surface temperature trend derived from the Landsat satellite imagery data. So this is one kind of paper. So in this paper, mainly they are identify about the trend, the land surface temperature trend, and they are used at the Landsat satellite imagery. So if you check the algorithm or data and method part, here you can see basically they are used at the Landsat collection 2 data, level 2 data, and further you can check the other algorithm. They use this type of equation for the trend, because in this paper they're also including about the trend. What is the trend for the LST? Okay. And they are calculating the trend chart, and they are calculate the data from 1984 to 2022. And they also calculate about the trend. Okay. If you check the other paper, suppose You can see there also calculate about the air temperature using the Landsat LST data. So basically, when you want to calculate the air temperature 2 meter height from the ground, so you can also calculate the LST. After that, you can also apply this algorithm, and then you can easily find out the result for the air temperature also. So further, you also explore this type of method and also apply using Google Earth Engine. Then you also get a lot of new things you can easily explore and also work with that. So here I already download some paper. So if I just open, so this is the one kind of paper you can see, algorithm for automated mapping of land surface temperature using Landsat satellite data. So in this paper, they are also using the Landsat 8 satellite imagery. So here you can see this is the algorithm about that. So basically they are take the band 10, band 4, band 5, and they calculated the NDVI, and then from the calculating the proportion of vegetation or fractional of vegetation or proportion vegetation, and further they are calculate the ground emissivity. It could determine of the ground emissivity, and then from the band 10 they calculate the top of atmospheric spectral radiance and conversion radiance to at a sensor temperature, and further they are calculating the LST and make the final LST result. So this type of algorithm they are creating here. Also, if you check this type of paper, suppose just I open it, just open the method and I'll zoom. So basically in this case, they are also used at that Landsat 8 satellite data. They're also calculating the okay, so this paper I think. Yeah. So you can see they are also calculating the LST. Basically, they are evaluating the land surface temperature with its association with land use land cover. So this is one kind of paper they are also published with land LST and also land use land cover. They are combined and they are make this type of paper. So now we talk about only for the LST. So basically, they use here this type of equation. Here you can see this is the equation about the land surface temperature. So land surface temperature in degree Celsius, this is the ST, land surface temperature in degree Celsius, equal to TB. TB mainly satellite brightness temperature. Okay, satellite brightness temperature. Its unit is the Kelvin, and then you can see 1 plus lambda TB, then rho logarithm if this is the emissivity. Okay, and there also you can see what is the emissivity. This is the formula about that, 0.004 PV mainly fraction proportion vegetation plus 0.986. Okay, and further there what is the PV mainly NDVI minus NDVI minimum divided by NDVI max minus NDVI minimum, then per square. Then we can easily find out the PV mainly fraction vegetation. This is the formula for the fractional vegetation. Okay, so now we did this type of work using Google Earth Engine. Okay, so from the Google Earth Engine, when you apply, first of all we need the satellite imagery. Okay, first step is that we are just taking the satellite imagery and we take the band 5 and band 4, mainly near infrared band and red band, and then calculated the NDVI, normalized difference vegetation index, then apply the vegetation proportion, and then we calculate the surface emissivity from here, and also take the band 10. Basically it's provide the satellite brightness temperature, and we calculate the brightness temperature. Further we apply the formula and also work with that. So basically all of algorithm almost similar, but some algorithm has some different types of things, but almost all of algorithm for Landsat 8 satellite data to drive LST is the similar. So now we'll show you the practical example. I hope you can easily get the idea how it will work. So let me open my code editor. First of all, we need a satellite imagery, okay, for your study area. So that's why we need to filter our image collection for the specific boundary. We already learned about that, how we can easily filter our image collection. Okay. So in this case, I want to apply this, suppose Landsat 8 satellite data or Landsat 9, Landsat 7 at the similar process. Sometime bands will be changed for the other satellite imagery. Landsat 8, 9 similar because their band is also similar for the Landsat 8 and 9. 8 and 9, this band are the similar. Okay, 7, 5, 4, 1 to 5, this band are some different. So that's why when you want to work for the Landsat 5, Landsat 4, Landsat 7, then you must need to check the band name because we find out the similar band Landsat 9 and Landsat 8. Okay, we find out the different for Landsat 5, 4 and others. So that's why when you want to work, first of all, you try to check the band and then you can simply put the band name. Then it will be more better. So now in this case, I want to work for suppose Landsat 8, this data. And we find out this type of reflectance, surface reflectance, top of atmosphere and raw image. So basically, when you want to monitor the land surface temperature, then we have to use the surface reflectance satellite imagery. We find out the very good result when you want to work with the surface reflectance. And this surface reflectance, we can easily find out the one band. This band name is the brightness temperature. So basically, this is the band. This band name is the surface temperature. Okay. So basically, this band STB10, this band help you to calculate the surface temperature. Degree unit is the Kelvin. Okay. So now we try to apply this type of algorithm and further we try to make the LST map for our study area. So now just simply import your study area, which area you want to work. So just simply import your own study area, which area you want to work for that. Suppose I want to work for this area. Suppose I want to work for this boundary, just click on here. Or any specific boundary, you can simply import and then work with that. Similar process, just apply. Suppose this is my study area, just import. And further, just I put the name, variable name, suppose ROI. So let me increase my screen. So just I simply import my study area, then just make a layer about this area. Just I add the layer map.add layer and call the ROI. And display the center of this boundary shape file. Just use their map.center object. Object is ROI and put the zoom level suppose 10 and click run. So now I find out my study area. Suppose this is my study area. And for this study area, I want to monitor for LST, mainly land surface temperature, as well as I also want to focus on the urban heat island. I want to identify this area is the urban heat island. Basically, urban heat island is one kind of phenomena. So this phenomena represent the higher temperature than neighbor place. Okay. So we also identify this type of urban heat island place, as well as we also identify for urban thermal field variance index. So basically, what's the impact? Where the high impact of urban heat island, and where is the low impact of urban heat island? We also monitor using the UTFVI index, mainly urban thermal field variance index. So I'll try to explain all of those one by one. I hope you can easily get the idea. So now, first of all, I simply define my study area. So now for this study area, I need the Landsat 8 satellite imagery where use the surface reflectance. So just copy the snippet ID from here. Just copy. And then paste here. Then give a variable name. I put the name suppose image. Okay. You can put any variable name. I put the name as the image. So now this is my image collection. This image collection simply filter for your study area. So we already know lot of process for filtering. Okay. So just anyone you can use for your own purpose and then take the satellite imagery. So for filtering, we already know about that, how we can easily filter. So first one is the filter bounds function. Mainly it intersecting with your whole collection for your study area. In this case, ROI, it's my study area. Then put here the filter metadata. Filter metadata mainly for filtering for specific properties. Suppose I need the data for cloud cover. Cloud cover less than suppose 1. Date. Basically, when you want to monitor the LST, what is the time period for LST you want to monitor? I put the time, suppose year of 2023, suppose 1st January from year of 2023, suppose December 31. So between this time period for 1 year, I want to make the annual LST. So that's why I take the 1 years for full year of 2023 from January to December. So now just I create the suppose median composite in this case and then clip with my study area. So clip with my study area is which one is that ROI. So now we display this satellite imagery. So just add a layer, map.add layer, and I want to display the image. Okay, the image variable. You can say I put the variable name is the image. So just now run the code. So one satellite image is added for my study area. We find out a problem. So let me check the problem. It show the empty date range not supported. So I think some mistake in here for the date range. Okay, so I put the 30 because 31. Okay, now let's check. What is the problem? Oh, sorry. We have to put the 2023. 31 is also okay. There is no problem because 30 December 31st. So network. So now we find out this type of satellite imagery for our study area. So it look like that. Okay, so now we add the visualization. We already know about that, how we can add the visualization for our satellite imagery. Just click on here and add the, I put here suppose red, then green and blue. It's taking suppose 98%. Just put in here and then apply. So now we find out this type of satellite imagery. Just I import it and copy this variable name and paste after the object name. Object is mainly image. I put the visualization parameter and third argument is for your layer name. I put the layer name, it's a image. So now this is the first step. When you want to work for the LST monitoring, we just need a satellite imagery. Okay. So in this satellite imagery, if you check how much bands are available, just simply print the image. So now it's computing how much image, how much bands are available. So here you can see this median composite satellite images, including total 19 bands. Okay, so if you check all of band name, you can see for SRB1 to all of bands are available in here. Okay, so we got our satellite imagery. So now from this satellite imagery, I just need only for those band for LST. I need the band 10, I need the band 5 and band 4. Okay. So basically these 3 band we need when you want to work for LST, land surface temperature. When you monitor, we need the near infrared, red and thermal infrared, mainly band 10. So now I want to just get this type of band and I calculate the NDVI. I make the NDVI. So previous class I discussed about that a lot of method to calculating the different types of index, different types of indices. We already know about that, how we can easily calculate the NDVI, how we can easily calculate the EVI, or how we can easily calculate the survey or any other index, how we can easily calculate using the Google Earth engine. We already discussed about that. So now we can easily calculate the NDVI. Suppose I have a image. So I have a image. So now I can easily make the NDVI and I can easily find out the vegetation index. So let me try to calculate the NDVI. So for that, just take a variable, suppose NDVI, and I call the image, and I put here that normalized, okay, and put here the band name, suppose SRB5 near infrared, and put here the red band SRB4. So we already know about that normalized difference function. Normalized difference function mainly calculated index only for the two band. Okay, suppose you want to calculate any kinds of index, they are only for the two band. Suppose NDVI, NDWI. So this type of formula we can easily calculate using the normalized difference. But some formula have lot of constant value, lot of band. So that's why you need to apply the expression. I already discussed about that, how we can easily calculate the expression. So now just I put the normalized difference, and I want to calculate the normalized difference between SRB5 and SRB4, mainly near infrared band and red band. So now it's automatic computed SRB5 minus SRB4 divided by SRB5 plus SRB4 and make the NDVI map and store it in here. So now further, if I just show the layer, so just put here map dot add layer and call the NDVI and click run. So now it make the NDVI map, and we can easily find out where is the high vegetation, where is the low vegetation. We can easily get it from here. So it show the gray color. If you want, you can also add the color. So just I click on here, and I just click on the stressing. It was 98%, and further click on the plated, so we can add the color plated. Suppose I want to display this type of color for the low vegetation, get it, then I want to show this type of suppose I want to put here this type of white color, or for the high vegetation show this type of green color. So apply. So now we find out, just import it, and we find out this type of map. So here you can see, well, just simply copy this vegetation parameter and further paste after the object name. So just I set the visualization parameter. Visualization parameter mainly it's one kind of color or symbology. I add the color. It's stored in this variable, and I put the layer name. Just put the layer name. Suppose it's a NDVI. So now you also calculate the NDVI. So now from this satellite imagery, we can easily detect for the vegetation. Where is the high vegetation? Where is the no vegetation? We can easily get this type of information from the satellite imagery. So basically, this type of green color, indicating about that vegetated area or vegetation. So you can see this type of green color. It's indicating about the vegetation. So this is our first step. We calculated NDVI. You can see this type of vegetation can get it. So this type of green color indicating about the vegetation. And this is our first step to monitor the NDVI. After calculating the NDVI, we need to calculate the vegetation proportion. So here you can see we need to calculate the vegetation proportion. Okay. So now what is the vegetation proportion? Okay. So vegetation proportion, if you check the paper, so we find out this type of formula for proportion of vegetation. This vegetation formula is that NDVI minus NDVI minimum value divided by NDVI max value minus NDVI minimum value and power 2. So when you apply this type of formula, we can easily calculate the proportion of vegetation. Okay. So after calculating the proportion of vegetation, we can easily apply in here. Okay. Surface emissivity. We are simply input this vegetation proportion, and then we can easily calculate the emissivity. Then we can simply input the emissivity in this equation, and finally we can just calculate the LST. So let's go. We just need to calculate the proportion of vegetation, and now we need to calculate the two things. One is the NDVI minimum value, another is the NDVI maximum value we need. Okay. So now we talk about that how we can easily calculate. Suppose for this study area, I want to calculate for high NDVI value or maximum NDVI value as well as also minimum NDVI value. If I just click on here and click suppose this type of vegetation pixel, we find out that this specific coordinate, what's the value? We find out the 0.361. So this is the value for this specific coordinate. But for the whole study area, I want to need the maximum pixel value of NDVI and minimum pixel value of NDVI. Then I can easily apply this formula. This formula mainly, NDVI minus NDVI minimum value divided by NDVI maximum value and NDVI minimum value, then power 2. Okay. So for calculating this equation, I need the two value, NDVI minimum value and NDVI maximum value. So now how I can calculate? So let's go calculate it. So for NDVI, just take a variable. Suppose I put the variable name is that max and I call the NDVI, and then I then put here that NDVI dot, I use a function, basically this function called the region. Okay, and I put all of argument one by one. So in this case, we are applying a function reduce region. Okay, so this reduce region function help you to calculate for any pixel. It can be maximum, minimum, or average for a specific boundary. So in this case, for this boundary, I want to calculate for minimum and maximum pixel of NDVI. So that's why just I apply this function reduce region. This reduce function computed the for any specific boundary for maximum, minimum, average, or standard deviation or any statistical pixel value. It can be calculated from here. Okay. So now after that, just make a curly bracket start and also curly bracket end, because I want to make a dictionary in here. And first of all, reducer. So now how I can reduce, I want to calculate for maximum. So put here EE dot reducer dot max. So now it computed the maximum NDVI pixel value. Then geometry mainly it's your shapefile variable name. Shapefile mainly ROI. Then scale is the resolution of your satellite imagery for 30 meter. Then it's not need, just remove it. Just remove. It's not need in this time, and it's optional. Okay, just remove it. So now if I just print the max and click the run. So now we find out the console tab and check the result. Okay, we face a problem. You can see it show this type of problem. It show that there are the too many pixel in the region. Okay, but max pixel allow only for this value. Okay, so when you face this type of problem, we need to mention about the max pixel. Just like copy the max pixels. And if you want, basically this type of problem we face when you want to work for the big study area. Okay, when you want to work with for the big study area, we face this type of problem. So now I put here the max pixel also, and I mention the value, suppose 1E13, value 1 into 10 to the 13. Okay, but normally max pixel allow only for this value. Okay, mainly you can see only allow this type of value, but in this case I just increase the value because it's my big study area. But if when you work with the for a small study area, then not need to mention the max pixels. But when you want to work for the big study area, you face this type of problem, too many pixels in the region, then simply increase the value. So in this case, I just put 1e13. Okay. So now just run the code and check what happened. So now here you can see we find out it's working, and we can get the result object one property. Just click on here. We can get the result 0.46. But this thing show as a dictionary. Here you can see it show the result as a dictionary. We find out the keyword and key value. Okay. So this is one kind of dictionary, but I need the result only for this number. I need only for this number without dictionary. So from this dictionary, I want to extract the value. So how I can extract the value? For extracting this value, just use here dot values function. Values. So now I got only for this number without keyword. Okay, when I apply the values. So now run the code again. So here you can see we can get the values without dictionary, but it worked as a list. You can see it show the list number 0. 0 mainly first item in our list. So 0, and then we put out the value. So that's why we can simply use a function get and put at the 0. 0 mainly serial number. So this is the serial number 0. Just put the 0. So if I run the code in this time, here you can see it just computed object and only show the number. Okay. So when we apply the values and apply the get function, then it easily remove the dictionary as well as also remove the list. So we can find out this type of normal value from here. But this number I want to use as a number. Okay. So for that, simply use here the e dot number function. Okay. So now it working as a number. So just run the code. You can see it show the number computing, and we find out only for this number. So now further, I can easily apply this number and also work with that for in our formula. So now apply the same process for monitoring the minimum pixel of NDVI. So let's go try to do it. For the same process we apply for making the LST for minimum pixel of NDVI. Just copy the same code and paste here and give a variable name, suppose mean, and I calculate suppose minimum. So just put here the mean. So now run the code. Okay, also print that. So just use that the print the mean. It will run. So we find out this type of result. You can see this is the minimum NDVI pixel value negative 0.235, and this is the maximum pixel value 0.460. So this value mainly for whole study area. So for the whole study area, from the whole study area, we calculated the maximum NDVI as well as also calculate the minimum NDVI. Okay. So now we can easily apply the formula for proportion vegetation or fractional vegetation. So you can see. So now we can easily apply this formula. Basically NDVI minus NDVI minimum divided by NDVI max value minus NDVI minimum value, then power 2. So now we can easily apply this formula because I already calculated for NDVI minimum and NDVI maximum. I already calculated. So now we calculate these things. So let's go. So calculating this type of equation, you can easily apply different method, but easiest method is that we can easily apply. Suppose I want to put the direct equation. So the code. Just take a variable. Suppose I put the variable, suppose FB, or you can put any name as a variable. I put the fractional vegetation, and I call the NDVI. This NDVI subtract with minimum value, then divided with maximum value, then subtract with minimum value. Okay, so just we are applying this formula. NDVI minus minimum value of NDVI divided by maximum value NDVI and minus minimum value of NDVI, and finally also have a power 2. Okay, so you also need to mention about the power 2 in the full equation. So for that, just bracket start and also close this bracket. Okay, so in the full equation we are just set the power power 2. Okay, but 2 is a number in Google Earth Engine. When you want to construct a new number, we have to use the function e dot number and put the 2. So now we are just applying a formula of fractional vegetation, mainly NDVI minus minimum value of NDVI, then divided by maximum value of NDVI minus minimum value of NDVI, and finally power 2. Okay. So now further, I want to display the layer of FV. Suppose just I put here map dot add layer and call the FV. Click on. So now it creates the one layer for proportion of vegetation or fractional of vegetation. You can easily get it from here. So now you can get this type of map for proportion of vegetation or fractional of vegetation. So if you want, you can also add the color. Suppose I add the color, then it look more better. Or if you want, you can also export all of layer as a GeoTIFF file format, and further you can also make the map using ArcMap or QGIS software. So basically in the ArcGIS, this tool, further I also explain in our fifth number day. Okay, fifth number day I also try to explain how we can easily work with ArcGIS and also QGIS software to create this type of map after downloading the GeoTIFF file format. Then you can easily get the more better idea how it works. Okay, so just I set the color. I put the green, suppose this type of color for vegetation. And so now it also added the proportion of vegetation we generate and also add the color. So now further just copy this visualization parameter and just paste here. Just paste here. And I put the name, suppose as a FV run. Color is also set with our layer. So we find out this type of layer of the fractional vegetation or proportion of vegetation. We can just get it. So just click on, you can see, and you can see here it show the band grayscale ND. Okay, so basically this is the default variable name. Okay, that is the default all time. Here you can see, if I just show the click on here, you can see it show the ND. Okay, if you want, you can also change this type of name. Okay, suppose I put a specific name, then it also will be more better. Suppose I just use the dot rename function after the equation, just put here the dot rename. Suppose I put the dot rename as a FB. Click run. So now if I check, and you can see it show the error. Okay, because when I just put the FV, this it also changed. Okay, so for that I just simply remove the previous one and I put the empty, and now run the code. So now it will be work. Just you can see it will be work. If I just click on here, we can get the band name is the FV because I put the rename. When I rename it, we can get the result as the FV, or you can put any name. So in this case, I put the FV. So now I set the color of the for the visualization. Suppose I put this type of color for that, and also increasing, just I put this type of white color, and then for vegetation show this type of green color or dark green. Yes, I put, and then apply. So now it will set it with that. I think this color is not more better. I want to put here this type of color, better for vegetation. We find out and also put the stressing. We have to select the stressing level. So 98%. Now apply. So now you can see we can get this type of map of fractional vegetation. So just copy the new visualization parameter from here. You can see it show the FV. Okay, but previous one is the ND. Okay, it's the default. But when I change the name, it show the FV band name. Just I copy and set with my object after the object. Just set. Just set. So now fractional vegetation is done. We calculate the fractional vegetation. So now we calculate the emissivity. Okay, so here you can see after calculating the fractional vegetation, we can easily apply this formula and calculate the emissivity. And you can see emissivity can be calculated by using this equation. You can also click on here, you can also get the citation about that. And this is the formula 0.04, 0.004 multiply with fractional vegetation plus 0.986. So in this case, we are just applying this formula and calculate for fractional vegetation. So let's go try to calculate these things, this type of formula. So basically in this formula, we find out the two constant value 0.004 and 0.986. So these two constant value, we simply store it in two variable. Further, we can easily use this variable and calculate the equation. So let's go try to show the practically. So for calculating the emissivity, just we take a variable, suppose A, and store it a number. Just I store it a number. So define a new number or construct a new number in Google Earth Engine. We have to use the function. This function name is ee.number. Okay, we already know about that. And I put the number 0.004. Further, I take the another variable, suppose B, and I put here ee.number and I put here the 0.986. So these two variable, I just store it into number, just store the two variable A and B. And further, I just take a variable, suppose EM equal, just I call the A, mainly 0.004. These things multiply with FV, mainly fractional vegetation. You can see mainly this layer. Okay, just I call the FV and I put here the fractional vegetation. So 0.004 multiply with FV and then add with 0.986, mainly B. So just I put here the B. We calculate this type of formula, 0.004 multiply with proportion vegetation plus 0.986. Simply I add. So we find out this type of emissivity. Okay, and if you want, you can also put here the dot rename function and put here the variable name. Suppose I put the layer name, suppose EMM. You can put any name and just I add the layer. So just map dot add layer and call the EM and click to the run. So now it calculated. Okay, we find a problem. This problem is that okay, we have to, let me check, put the fractional vegetation FV multiply with A. So I hope not okay. So next word, because we also put here the parenthesis in here. Okay. So that's why we have to put the parenthesis, mainly always in the right value we are just put the parenthesis. So we put here this type of things look like that of surface emissivity. So now if you want to also add the visualization, just click on here. And now here you can see it show the EMM because I put the rename. Okay, when you put the rename, we find out the new name in here, EMM. Or you can put any name as the layer as the band name. Okay. Further, just stressing. And we add the color. Suppose for where is the low, show as the blue. Greater than show this type of green. Greater than show this type of yellow. And where is the high, show as a red color. Okay, red is indicating about the high surface emissivity area. Just apply and also import and further copy the variable name, copy this variable name of emissivity layer and paste after the object name. Just paste here and I put the layer name. Suppose I put the layer name is that EM. Click to the run. So now finally we calculated the emissivity. So basically this is the emissivity map, and here we find out that this type of red color indicating about the high emissivity. Okay, this type of red color indicating about the high emissivity area. We can easily find out from here. So this is the map for emissivity we calculated. So after calculating the emissivity, we have to calculate the another things, the brightness temperature. Okay, so now if you check the paper, so we calculate the emissivity. So now almost this is our final formula. In the final formula we are just need only for the TB mainly brightness temperature. Okay, so we already calculate all of those things, so now we need only for the TB. So if I calculate the TB, mainly satellite brightness temperature, then I can easily apply for full equation for LST. You can easily apply for the LST easily in Google Earth Engine and calculate the final layer of LST. So now I will show you that how we can easily calculate the thermal band, mainly brightness temperature, we calculate in Google Earth Engine. So let's go. So for that, just take a variable. Suppose I put the variable name is that thermal equal. So basically thermal band come from my satellite imagery. Okay. And I already make the satellite imagery, and this is my satellite imagery. So from this satellite imagery, I just need to call a band. This band name is that you can see the band name from the information sheet of your satellite data, STB10. Okay. So this is the band. This band mainly provide you the surface temperature we can get from the surface temperature, and this unit is the Kelvin. So further we also try to change it in the degree Celsius. So we find out this type of thing. So just I call the STB10. So just I call the variable name image because this satellite image is stored in this variable, and I just use here the dot select function and put here STB10. Okay, mainly brightness temperature. So now this band we need to reproject the scale value. Reprojected the pixel scale value. For reprojected, just multiply with scale value. So you can easily get the scale value from here. This is the scale value of STB10. Copy and paste here and add with offset value. Basically, this is the offset value 149. So this is the offset value. Simply copy and add here. So now our brightness temperature band is ready. So now if you want, you can simply just add the layer. So just put here map dot add layer and call the thermal. Now run the code. Let's show this type of color. So we try to add the visualization for that brightness temperature layer. Let's show the STB10, just stressing. And I put here, suppose I add the low as a blue color, greater than show as a yellow green color, or you can put any color combination or yellow color, and high show as a red color. Then apply. So you find out this type of map, just import and copy this visualization parameter, just copy. And paste here and put it, it's a so now we calculated all of parameter such as you can see the NDVI, then proportion of vegetation or fraction of vegetation, then surface emissivity, as well as calculate for the thermal band we calculate. So now we can easily apply this type of formula. Mainly we can easily calculate it, this type of formula, and get the final equation of LST. Okay. So now this formula here you can see we find out that TB mainly we already calculated the TB mainly satellite brightness temperature in the Kelvin unit we already calculated. Then lambda, so lambda wavelength emitted radiance, so basically this is the value 11.5 micrometer, and rho it's also constant value 1.438 10 inverse 2, and emissivity we already calculated the emissivity we already calculated using this formula. Okay, so now we can apply the full equation and calculate it. So basically 273.15, it just simply subtract to get the result in degree Celsius. Okay, so when you subtract this value we can get the result in degree Celsius. So now we try to compute it the final equation and then check the result for LST. So just take a variable, suppose LST, and then call here the thermal. Call the thermal band and apply the expression. Okay. So in this expression, we need to apply this type of formula. This type of formula you can simply apply and calculate the final LST layer. So let's go try to